All right, so we're going to go through an example, actually two, where we're going to compare and contrast sulfur dioxide and sulfur trioxide. For each, you're going to draw the Lewis structure, you're going to determine the electronic geometry, you're going to tell me the molecular geometry, and you're going to tell me if it's polar or not. So we will start with SO2. So first off, get the electron count, or the valence electron count. Sulfur normally has 6 valence electrons. Each of the oxygens contributes 6 as well, giving you a total of 18. So let's get the Lewis structure. The formula tells us that sulfur is going to be in the middle and bonded to 2 oxygens. So that takes care of 4 of the 18 electrons. The rest of them put 3 unshared pairs around each outside one. So we've got 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 2 more, so they go on the inside, and that's the 18 electrons. So let's analyze this structure. From an octet standpoint, the oxygens are good, but the sulfur isn't. And let's talk about the formal charges. So for this oxygen right here, oxygen has normally 6 valence electrons. You can assign 7 to it in this structure, so it has a formal charge of -1. In the case of sulfur, again, usually has 6 electrons or has 6 valence electrons. You can assign 1, 2, 3, 4 of them in here, and that is going to give us a formal charge of +2. Both of these we change by taking some of these unshared electron pairs and making them shared electron pairs. And remember, whenever you do this, do it from outside unshared pairs to inside unshared pairs. All right, and so let's go back to right here. So I'm going to just clean this up a little bit here. So that's going to give us a sulfur double bonded to the oxygens. Like that. Oh, I have one more unshared pair. We want that, and we want that. So everything is octet happy. The sulfur actually has 10, but that's okay. And oxygens have 2, and there's no formal charge. So that's actually about the best you can do for sulfur dioxide. Now, how many electron domains? So we've got 3 electron domains. I just call them EDs here. Remember that the multiple bonds count as 1 domain, and we have the unshared pair on the sulfur. So that means that our electronic geometry is going to be the magic shape for 3 electron domains, which is trigonal planar. And that actually looks, it's going to look something like that. With the electrons up here. And so the molecular geometry, you would call this shape, is bent. And so then the next question is it polar or not? And that's actually the next question and also the last one. So let me get my black out. So these bonds are polar. Oxygen is way more electronegative than sulfur. So they actually start from the sulfur, point to the oxygen. So the dipoles look like that. So then where are the charge centers? The positive one is the easy one to figure out because only the sulfur is going to be the one with the partial positive charge. So the center of positive charge is there. The center of negative charge is going to be, so the oxygens have the partial negative charge. So the center of the negative charge is going to be between the oxygens. Those are not the same points in space. So this molecule is polar. All right. So take a step back and think about this. Over the past 2 days, you have learned to go from this to that right here. I give you a formula, you give me a shape, and then you tell me if it's polar or not. So you have learned a lot in the past week. So let's do the same thing for sulfur trioxide. And how about hit pause, give it a shot on your own. And let's do this right here. And so I am just going to give you the Lewis structure for sulfur trioxide, because I think at this point you should be able to do it. So in this case, sulfur trioxide, you should end up with 3 sulfur oxygen triple bonds with 2 unshared pairs on each of the oxygen atoms. Now, so let's do the geometry now. So we've got 3 electron domains. Which means that the electronic geometry, which is right EG here, is also going to be trigonal planar. And since there aren't any unshared pairs in this case, the molecular geometry is also trigonal planar. Now, the last thing, is it polar or not? So these bonds are polar. The dipoles, oxygen is more electronegative. So the oxygen atoms have the partial negative charge. The sulfur atoms have the partial positive charge. The dipoles point from the sulfur to the oxygen in this case. So as before, the center of the positive charge is the easier one to figure out because there's only one atom with the partial positive charge on it, and that's the sulfur, so put the blue dot there. And the center of the negative charge is the center of all of the oxygen atoms, and that also happens to be the sulfur atom as well. So those two are coincident in space, which means that this molecule is polar. So even though the individual bonds are all polar, the molecule as a whole is not polar. And one more thing I want to add is that if none of the bonds in a molecule are polar to begin with, there is no way that the molecule is polar. If the bonds are polar, there is a chance that the molecule overall is polar, but as in this case, there is also a chance that the overall molecule is not polar as well. All right, and so to summarize with nice pretty results, so this is kind of what sulfur dioxide looks like. And sulfur trioxide looks like. The molecular geometry is trigonal planar bent for sulfur dioxide, trigonal planar for sulfur trioxide. The charge distribution, charge centers, polar, charge distributions, charge centers, positive, negative, nonpolar. All right, so make sure you do the homework, you do the examples. This actually becomes fairly easy after a while, and we will see you next time.